Hello all, I'm back with another video, and this is the International GCSE from November 2025, which is the most recent available paper I was able to find. And this is paper 2, okay, from your curriculum. And one thing I want to mention before we start is that you can see that you guys have 1 hour and 15 minutes to finish this. So my general recommendation to papers like this is that if a question awards, say, 10 marks, it should take about 10 minutes. So you should um, estimate that a question will take you about a minute per mark it awards, if that makes sense. And this is the second paper from this level I'm uploading. I received comments saying that they find these videos useful, so therefore I prepared one more paper. And anyway, let's dive in. So there are some formula that you can use in the first page here. And let's start with the first question. I think there are 8 questions in this paper. So I solved this paper a few days ago, so I forgot how many questions there are. So let's dive in. So question 1. The diagram shows the apparatus used to investigate electric charge. The equipment is viewed from above, okay? Ball 1 and ball 2 have a positive charge. Ball 1 is fixed in place, okay, this one. So ball 1 is fixed, in place. So this one that I marked with a cross, okay? Ball 2 is attached to a rod that can rotate about point P. This is point P. Okay. Ball 2 does not move. Okay. State in terms of charged particles how the balls have become positively charged. So they probably lost their electrons. Okay. So the balls lost electrons, hence they now have a net positive charge. And I don't know if they tell you these things in your classes, but most objects in nature are electrically neutral. Okay, so even if they lose a little bit of charge, they become charged with positive charge if they lose electrons. Okay, hope this is useful. So let's move on. Part B. Ball 1 exerts a force F of 0.57 newtons on ball 2. State the value of the force exerted on ball 1 from ball 2. Okay, so since electrical repulsion obeys Newton's third law, the force is the same, like 0.57 newtons. I'm sorry, I don't know why I hesitated, and it's in the opposite direction. So 0.57 newtons in the opposite direction. And we can write in parentheses that they obey Newton's third law. Okay, and 3 means Newton's third law. And if you want to draw the forces, so there is a force like that. Okay, so okay, let's move on. Calculate the moment on the rod from force F about point P. Okay, so we see that we are 4.2 centimeters away from the pivot point P, and this force is perpendicular to the rod, so it exerts a moment of, let's call it M, it's the moment, 0.57 times 4.2, and I didn't convert to meters because you see that they want the answer in newtons per centimeter, times centimeter. So this is Newton's centimeters, and the evaluation is 2.39 Newton centimeter, which is about 2.4 Newton centimeters, which you can write here. Okay. Part 3 now. State the magnitude of the moment about point P due to the force from the spring. So since moments are balanced, because we are told that the rod is not moving and ball 2 is not moving, okay, so we have a balance of moments, okay, so since moments are balanced, the moment is also 2.4 newtons centimeters, okay, so you can write here 2.4. And question 4, before we go to part 4, let me comment on this. So the force from the spring, okay, they have it there, okay, sorry. So I don't need to do anything. For a moment I was gonna draw the force, but okay, it's drawn, so that's good. So let's move on. Draw an arrow on the diagram to show the direction of the force that the rod exerts on the spring. So it's the same idea as with Newton's third law. So the spring exerts this force upwards on the rod. Therefore, the rod exerts this downwards force, which is equal and opposite on the spring, okay? Which is what they are asking. And this was question 1, okay? So let's move. Okay, question 2. This question is about gravitational field strength, okay? Which is en vogue these days, as we have the launch of Artemis 2, which is gonna fly by, I believe, by the moon. I mean, they're not gonna land. I don't know if they're gonna land in the future, but I mean, the technology for that relies heavily on calculating the gravitational field strengths of celestial objects very accurately. Okay, so the table shows gravitational field strengths at the surface of 4 different planets. The planets have the same mass but different diameters. Okay, so this is actually a key here. So the same mass, and you will see how that is important in a moment. So let's move to the first question, and you can see that the first planet here is Earth, pretty much. So anyway, give a reason why a scatter graph is the correct way to display this data rather than a bar chart. Okay, so it works best, okay, because both the diameter and G, the gravitational field strength, are continuous variables. Okay, you use bar charts or pie charts or things like that when you don't have continuous variables, when you have discrete variables that can be counted, like 1, 2, 3, 4, 5. Okay, so that's the answer. Part 2. A student claims that the relationship between the gravitational field strength and the diameter of a planet is given by this formula: gravitational field strength times diameter squared is equal to constant. Using data from the table, evaluate the student's claims. Okay, this is the table over here. So I'm going to copy the values and see if this is true. So for the first planet, we have G being 9.8, the diameter being 13,000 squared. And this is kilometers. And I keep the kilometers because it's convenient. So this evaluates to 1.66 times 10 to the 9. And then it's newtons, kilometers squared over kilograms. Okay, these are the units. For the second planet, we have 5.1 times 18,000 square is being equal to 1.65 times 10 to the 9 newtons, kilometers squared over kilograms. So this is a good sign. Okay, I mean, it's very similar, very close. The third planet, 3.8 times 21,000 squared, gives us 1.68 times 10 to the 9 newtons, kilometers squared over kilogram. And for the last planet, we have 2.9 times 24, I believe, yes, okay, 24,000 squared gives us 1.67 times 10 to the 9 newtons kilometer squared kilograms. So the student is right. You can see that the value is constant, but you have to be careful. I don't know if you learned this. I think you don't learn this yet, but the gravitational field strength is equal to the gravitational field constant, so that's a constant, times the mass of a planet over the distance squared. So the reason why this works is because the planets have the same mass. Okay, if they didn't have the same mass, this will not be constant. Okay, so I told you in the beginning that you will see how the same mass mentioned here will be important in this problem. So this is where it made its appearance. So part B, the diameter of a planet affects the gravitational field strength at the surface of the planet. Which of these is also a factor that affects gravitational field strength? Okay, we just said that the mass affects it. Okay, I gave you the formula. I think you learned about this at the A levels. Okay, so you don't learn about this at the GCSE level, but it's good to know. So mass is the other important factor. And actually the other answers, okay, this is one thing I noticed with the Edexcel exams. Sometimes in multiple choice questions, you can figure out the correct answer just by inspection, using the lawyer's way, as I call it. So lawyers usually arrive at the conclusion by eliminating all wrong answers. So here, for example, absolute magnitude makes no sense when it comes to gravitational field strength. I don't even know what they mean by absolute magnitude. Okay, color. I mean, color refers to stars, but G is something that can be calculated for any celestial object, including planets, stars, black holes, whatever. Okay. And then specific heat capacity is also totally relevant. So options A, B, and D are totally wrong. Okay. So even without knowing about what I just mentioned, you can find the correct answer. So this was question 2. By the way, I answer to all comments I receive unless they are obnoxious, because sometimes there are some spam messages from what I understood. I'm still new in YouTube, okay? So any questions you have, ask me in the comments and I always reply, okay? So this was question 2. Let's move on. Okay, question 3. The diagram shows some of the parts of a hydroelectric power station. Water enters the turbine with a momentum of 120,000 kilograms times meters per second. State the formula linking momentum, mass, and velocity. So momentum is mass times velocity. Easy peasy. Part 2. A mass of 14,000 kilograms of water enters the turbine. Calculate the velocity of the water as it enters the turbine. Okay, we are given the momentum in the beginning, so we can just use P, momentum is m times velocity. Therefore, we need velocity, which is momentum over mass. So 120,000 over 14,000. So these zeros cancel. And we have momentum is given in kilograms times meters per second. And then in the denominator, we have kilograms, so kilograms cancel. And we find 8.57 meters per second, which is about 8.6 meters per second. Okay. Part 3, the 14,000 kilograms of water leaves the turbine. This water has a momentum of 63,000 kilograms times meters per second after it leaves the turbine. The turbine exerts a force of 6,100 newtons on the water. Calculate the time taken for the water to pass through the turbine. So here is where you use the concept. Okay, the problem with me solving these papers is that I haven't actually taught at the GCSE level. So let me see if they give you, there is a formula that you need to use related to, which is Newton's second law pretty much, okay? This is what we will use, but let me see. Yes, they give it to you. So this is what we need to use. Okay, this is Newton's second law. So force is change in momentum over time taken. So that's the formula. Okay, so we know the force, we know the initial momentum, we know the final momentum. So we need to solve for time to find the answer. Okay, so let's go back over here. So force is, as we saw, the final momentum. Sorry, the initial momentum minus the final momentum over the time taken. Let's see. Let's take a look at the formula again. So yes, V is the V and U. Okay, good. So let's go back. Here. Okay. So time is 120,000 again, minus 63,000 over the force, which is 6,100. So this yields 9.34 seconds, which is about 9.3 seconds. Okay, that's the answer. Now, part B. As the water passes through the turbine, energy is lost from the water's kinetic energy store. Explain what happens to the energy lost from the water's kinetic energy store. So energy is transferred from the moving water to the turbine. Okay, the kinetic energy store of the turbine increases as it spins. So the kinetic energy store of the turbine increases as it spins faster. Okay, some energy is also transferred to the thermal store of the turbine and the surroundings. Okay, so this is a complete answer for this question. Okay, hydroelectric, power is an example of a renewable source for the generation of electricity. Give two examples of non-renewable resources for the generation of electricity. So oil, gas, and we can write also uranium, plutonium, etc. I mean, there are many other things that are not renewable. So this was question 3. Question 4. This question is about sound waves. Question A. Describe an investigation to measure the frequency of a sound wave with an oscilloscope. You may draw a diagram to help your answer. Okay, so in fear, I'm going to run out of space. So let's start writing from up there. So use a microphone, since you're going to study sound waves. Okay, use a microphone, excuse me, connected to an oscilloscope. Okay, make a steady sound so the oscilloscope shows a clear repeating waveform. Okay, so make a steady sound so the oscilloscope shows a clear repeating waveform. Okay, find the period by measuring the horizontal length of one wave, or better still, many waves. So of one wave, or better still, more waves. Okay, so you can find the period that way. Convert the number of squares into time using the time scale. If you measure several waves, divide by the number of waves to find the period. Okay, use frequency is equal to 1 over the period to calculate the frequency. Okay, and we didn't use any diagram, but if you did, you can show an oscilloscope. It looks like this. There's a screen like this with squares that allow you to measure. Let's use a different color. So maybe there is a waveform like that. So you can measure the amplitude here. So amplitude, and you can measure the time in this scale. And then there are knobs that you can use, something like that, to modify the amplitude and the time. And you can connect your microphone like this. So over here, can I draw a microphone? Don't know, something like this. So looks like a torch or a cigarette, but okay. And maybe you can sing in the microphone, like I don't know, your favorite singer. So yeah, you can write in the comments who your favorite singer is. Okay. And guys, please subscribe. I mean, from what I noticed, 85% of the people who watch these videos are not subscribed. So it's kind of sad. So let's move on to part B. The diagram shows an oscilloscope screen. One square in the x direction is 0.5 milliseconds, and one square in the y direction, I mean, I'm reading the information over there, is 0.5 volts. Estimate the period in milliseconds of the wave. So you can see, you can count. So to find the period, we have to find how many squares there are between two peaks or between two valleys. Okay, so it's the same thing. So I tried to do it with the peaks. So you can see that there is 1, 2, 3, 4, 5, and then maybe you can add another half. So I estimate that this to be 5.5 squares. Okay, so 5.5 squares times 0.5 millisecond per square yields 2.75 milliseconds. So over here you can write 2.8 milliseconds. Okay, and then the frequency is 1 over the period. So Okay, calculate the frequency of the wave. This is simple. The frequency is 1 over the period, so 1 over 2.75 times 10 to the negative 3. And then this is seconds to the minus 1, which is, of course, hertz. So 363.6 hertz. So over here you can write 6.64 maybe. So this was question 4. Okay, question 5. The diagram shows a cross-section of a solenoid. And the key here is that with crosses, we have the part of the coil that goes into the paper, and with the tip, with the dot, we have the current that comes out of the paper. Draw one field line on the diagram to show the direction of the magnetic field. So the trick here is to use your right hand and put your thumb points in the direction of the current, okay? So in this case, where the crosses are, your thumb should point into the page, okay? And then your palm rotates. I mean, if you make a rotating motion, you will see that the direction is this one, okay? And your palm points in the direction of the magnetic field generated by that current pretty much, okay? So it will look like this. And then similarly, if you make your thumb pointing outwards for this part where the current comes out of the page, then you will see that your thumb rotates in this direction, okay? And now, if you keep making those circles, they will meet over here and they will create a magnetic field that points out of the page. Sorry, what am I saying? To the left, okay? Sorry. So this is the magnetic field generated, okay? So you can make the lines go like that. And the idea is that, let me draw a big circle. So for example, the magnetic field generated by this part, okay, points to the left. And then the magnetic field generated from this current, let me think, points like that. Therefore, where they meet, you sum them, okay? So you create a magnetic field that points to the left of the page. I hope this makes sense. If it doesn't, ask me in the comments. Okay, question 2, use the field line to determine the end of the solenoid. Which end of the solenoid is the north pole, and label it on the diagram. So let's use green. So the north pole is where the magnetic field lines come out. So this is the north pole and this is the south pole. Okay. Part B, a transformer consists of two solenoids and an iron core. This is the label on the transformer. We have the number of turns on primary coil being 180. Number of turns on the secondary coil is 345. Output voltage is 230, and output power is 320 watts. State the formula linking input voltage, output voltage, and the turns ratio. So, and this is the voltage in the primary coil over the voltage in the secondary coil is simply the number of turns in the primary coil over the number of turns in the secondary coil. Do they actually give you this formula? I'm curious. Again, as I said, I never actually taught GCSE Physics. Okay, it's not here. I don't see it. Let's go to the back of the paper. Let's see if it's over here. Do you see it? I don't see it. No, so this is something you have to remember maybe? No, here. This is the formula. Okay. No, this is not the formula. Sorry, this is for current and power. So this is actually the formula. Okay, so they actually give you the formula, guys. So you have to just go back to the back of the paper and copy it. Okay, so calculate the input voltage for this of this transformer. So the voltage in the primary coil over 230, which is the voltage of the secondary coil or the output, is equal 280 over 345. So the voltage in the primary is 120 volts. Okay, so we actually increase the output voltage. By the way, for the record, 120 volts is what they have in the United States, where I lived for many years, and 240 is what they have here in Cyprus. I believe in England as well. So we used to be a British colony, so maybe it's the same. So I don't know. Let me know in the comments. Part 3, give the name of this type of transformer. This is a step-up transformer. And the naming is obvious. I mean, we increase the voltage, okay? 4, when the transformer is in use, there is a current in the primary coil and in the secondary coil. State the type of current in the coils of the transformer. So it's basically AC current, okay? AC DC. Sorry, that's the rock band. So transformers work with AC current. Okay, this was question 5. Okay, question 6. Galaxies A, B, and C are different distances from the Earth. Galaxy A is moving away from the Earth with a velocity of 1.7 times 10 to the 4 kilometers per second. The reference wavelength of light, for light, arriving at the Earth from Galaxy A is 506 nanometers, so that's greenish. Calculate the observed wavelength for the light arriving from Galaxy A, and they give you the speed of light in kilometers per second. So, the change in wavelength over lambda is equal to the velocity of the galaxy over c. And this is from my A-level classes. I don't know if they give you this exact formula here. Let's check actually. Okay, I don't see. It's over here. So let's unbox this because we already used it. And yeah, this is what we need to use. The change of wavelength over the wavelength is equal to the velocity of the galaxy over the speed of light. Okay, so lambda minus lambda naught over lambda naught is v over c. Okay, this is what we will use. So let's go back. So we have lambda minus lambda naught over lambda naught is equal to v over c. So let me think. So lambda minus 506 over 506 is equal to 1.7 times 10 to the 4 over 3 times 10 to the 5. So we have, let me use a clean page, lambda minus 506 over 506 is equal to 0.0566. So we have lambda minus 506 is equal to 506 times 0.0566. So lambda minus 506 is 28.67. So lambda, the one we will see, is 534 times 67 nanometers, which is about 534.7 nanometers, and this is redshift as the galaxy is moving away from us. Okay, so if it moves towards us, we will see the blue shift. Therefore, the observed wavelength will have a smaller wavelength than the normal one. Okay, so part B. Galaxy B is twice as far away from the Earth as Galaxy A is from the Earth. Galaxy C is 4 times far away from the Earth as Galaxy A is from the Earth. Explain how the velocities of galaxies B and C are different. So the universe is expanding. So galaxies are moving away from Earth. Okay. Recession speed, okay, increases with distance. Okay. Galaxy B is twice as far away as A. Okay. So the speed of Galaxy B is 2 times the speed of Galaxy A. Okay. Galaxy C is 4 times as far away as A. Thus, the speed of C is 4 times the speed of A. Okay, and then finally, let's use the clean page. So we're moving over here. So from here, we go here, okay? So Galaxy C is, oops, Galaxy C is faster than B. So VC is 2 times the speed of B, okay? And this is because they are farther away from each other. So let's move on to part C. The universe started with an event called the Big Bang, not the series, the actual thing. Explain how evidence from cosmic microwave background radiation shows how the temperature of the universe has changed since the Big Bang. So, and by the way, this cosmic microwave background was discovered by Penzias, I think. These guys were engineers, and I think they discovered this by accident. They were trying to investigate something else. So, but don't quote me on this because I haven't studied this in years. So please check my facts. Okay. So the universe has expanded since the Big Bang. Okay, as the universe expands, lambda from cosmic wave, so from cosmic microwave, excuse me, radiation increases. Okay, longer lambda means, my handwriting is so horrible, excuse me guys. So longer lambda means lower temperature. Okay, so the universe must have been hotter in the past and cool down over time. All right, so this was question 6. Okay, question 7. A student investigates how the temperature of a metal block varies with time as it is heated. Okay, the student measures the temperature of the block at 5-minute intervals for a total of 30 minutes. The graph shows the student's results. Okay, so at 450 degrees Celsius, it melts pretty much. Okay, give the name of a piece of equipment that the student could use to measure the time during this investigation. A stopwatch will do. Part 2, which of these is the dependent variable in this investigation? So the dependent variable, I mean, especially when they give you a graph, is always in the y-axis, okay? So that's the temperature of block. So that's option B. Okay. Part B, the energy supplied to the block is 440,000 joules. Calculate the mass of the metal block when the temperature of the block increases from 45 degrees to its melting point of 450 degrees Celsius. And for the metal, the specific heat capacity is 910 joules per kilogram per degree Celsius. So the energy increase is given by the specific heat capacity times the mass times the change in temperature. So we have to solve for mass. So the mass is energy over C times delta theta. So let's come over here. So the energy is 440,000 joules, 440,000 joules. And whenever I work out problems, I put the numbers to the left and the units to the right. Okay, so this is a convention I use. So C is 910, and we have joules, and then kilograms and degrees Celsius in the numerator, and then times delta theta, which is 405 degrees Celsius. And a special note for delta theta in degrees Celsius is the same as delta theta in Kelvin. Okay, so joules delete, degrees Celsius delete, and if we carry the calculation, we find 1.19 kilograms. So down here we can write 1.2. Okay, the metal block melts and then the liquid metal boils to become a gas. That sounds terrifying. So, I mean, because it's a metal. So, describe the motion of the particles when the metal is a gas. So, gas particles have high speeds, okay, and they move randomly. Okay, and part D suggests two changes to the graph if the student had used a different metal in their investigation. So we will have a different gradient, and also different melting temperature. So if we come to the graph, maybe another metal would look like this. Okay, so different temperature, or maybe like this, and then like that. Okay, so we'll have both a different gradient. Let's use red. So different gradient, different melting points, etc. Okay. All right. This was question 7, guys, and let's move on. Okay, a question about the nuclear power station. And for those of you who never watched the video from me, I have a PhD in nuclear physics, and it's my favorite subject, pretty much, in physics. That and in general, excuse me, I like quantum mechanics, like microscopic particles and equations and mathematical physics, things like that. So the photograph shows a nuclear power station. A chain reaction releases energy inside the power station. Explain how the fission of uranium-235 can set up a chain reaction. So the way I describe it, I don't know what they teach you at school, but uranium-235 is the useful nuclear fuel, and uranium-238 is not as 238, excuse me, is not as useful. And the way I distinguish the two is that you can picture uranium-235 as dry wood, burns easily, whereas 238 is like green wood. It can still burn, but you need a lot of energy to burn it. okay, because it has a lot of water. So, I mean, it's not the same analogy, it's just an analogy because we are talking about nuclei here, okay? So, uranium-235 easily absorbs neutrons, okay? The uranium that absorbed a neutron is unstable, or better yet, becomes unstable, okay? Becomes unstable. Okay. The unstable uranium breaks into two lighter nuclei, releasing neutrons. Okay, let me use a clean page because I ran out of space. The neutrons are then absorbed by other uranium-235 nuclei, triggering a chain reaction. So what's going on is that if this is a uranium-235 atom and we fire a neutron towards it, it then splits into lighter nuclei and then it releases more neutrons. And those neutrons go on to find other uranium-235 nuclei, which split again. And they release more neutrons. Neutrons are red in this picture. Okay. So this triggers a chain reaction. Okay. So this is the idea. Let's go back to the second question. Explain how nuclear fusion is different from radioactive decay. So in radioactive decay, the nucleus decays into another nucleus. Okay, releasing alpha, beta, or gamma radiation. Okay, let's go to the clean page. Okay, so the second part continues here. So in fusion, lighter nuclei fuse into one heavier nucleus, with, of course, the example of the sun. You don't need to write this in your paper, but I'm just giving you an example. So, for example, you have deuterium, which is a hydrogen nucleus that contains one more neutron. Okay, so maybe these two nuclei fuse into helium-4. Okay, and you can see that we have 2 plus 2 becomes 4, and then we have one proton, and one proton makes 2 proton. Okay, so we have to balance this equation. Okay, part C, an isotope of hydrogen is used as a fuel for nuclear fusion. The nuclear equation shows how this isotope of hydrogen can be manufactured. Complete the equation by giving the missing information. Okay, so first of all, a neutron doesn't have a charge. Okay, so 0 for the atomic number. So we have 0 plus 3. As far as protons go, we have 3 in the left-hand side, and then 1 plus 2 is 3 in the right-hand side. And then the mass number is 7 in the left-hand side, 1 plus 6 is 7. Therefore, we need 3 over here. Okay, so that's tritium. That's how it's called. Okay, part D. Explain why nuclear fusion can only happen at high temperatures and pressures. So we need to overcome the electrostatic repulsion. Okay, repulsion. Therefore, we need high kinetic energies, hence high temperature. Okay, and also we need high pressure to bring nuclei closer. Okay, so that's the answer. And then finally part, no, it's not finally, there is one more. I mean, question 8 continues on the next page. So part E, part 1, which of these is the time taken for the number of undecayed nuclei in a radioactive isotope to halve? That's half-life. Okay, option C. And then this is the final question. The isotope of hydrogen is radioactive and has a half-life of 12 years. Okay. A sample of the isotope has an activity of 72 kilobecquerels. Calculate the activity of the isotope in the sample after 60 years. Okay, so we start with 72, and then in 12 years, so we have 72 kilobecquerels, and then when 12 years pass, so 12 years, we will have 36 since it will halve, right? And then in another 12 years, so 24 years in total, we will have 18 kilobecquerels. And then in another 12 years, we will have 9 kilobecquerels. And then in another 12 years, we will have 4.5 kilobecquerels. And then in another 12 years, we will have 2.25 kilobecquerels. Okay, you can see that 12 plus 12, 24, 36, 48, 60. Okay, so 2.25 is the answer. Okay, and this was paper, which one was it? Paper 2 from November 2025. Please let me know in the comments if you find these videos useful. Please like and subscribe. Hopefully I will come up with more solutions like this in the future, and see you in the next one. Bye.